In the previous video, we discussed concurrency and how threads have the ability to mutate each other's values in undesirable ways. In this video, we're going to take a look at the NSThread class and how we can utilize NSThread to queue up tasks for the system to schedule. We'll also demonstrate how two threads can interfere with one another if used improperly. The Foundation framework provides a class named NSThread, which greatly simplifies the creation and management of new threads in our programs. While NSThread manages the setup and disposal of threads for you, it does not provide any protection from other threads. Let's start by creating a new Xcode project. We'll select OS X application and create a command line tool for this example. Add a name for your project and click Next. Choose a place to save and click Create. We'll start by making a class that has a single property that will hold our current value, and then a function that will increment that value from 0 to 5,000 and then decrement back to 0 again. I'll create a class named Threading. NSThread utilizes the Objective-C perform selector, so we're going to need to expose our class to Objective-C by either subclassing NSObject or by using the obc keyword. In this example, we'll simply subclass NSObject. Now that we have our class defined, I'll add a property and give it a value of 0, and for brevity, I'll paste my function in. This rise-fall function has two for each loops. The first iterates over a range from 0 to 5,000, and then increments our counter accordingly. The next for each loop decrements our value back to 0. Now, I could have done this example with just one for loop, of course, but I wanted to give our threads more opportunities to intermingle. Now that we have our threading class fleshed out, we'll add a new variable that will hold an instance of our threading class, and then we'll call our rise-fall function, build and run, and you'll see that your program quickly returns 0, as to be expected. No matter how many times we run this function, we'll always arrive back at 0. We can even add subsequent calls to our rise-fall function, and as we see in our console, we always arrive at 0. This is because our rise-fall function performs our loops synchronously, meaning that when our first call to count.risefall is made, our application waits until it completes before making the second call. This is because both of our calls are operating on the same thread. Now, we can move our second call to rise-fall off of our main thread and onto its own thread to call this function concurrently by using the NSThread class from Objective-C. So let's create an instance of NSThread and call the detachNewThreadSelector method, which takes a selector, a target, and optionally an object. So for our selector, we'll call our rise-fall method, and we're going to target our count instance of our threading class object, and then we won't be passing an object, so we can just set that to nil. Now NSThread runs asynchronously, meaning that when we call it, it doesn't wait for its operation to complete before our run loop fires our count.risefall. Since we can't guarantee that our NSThread will finish first, our main thread has the potential to finish first and end the loop before our NSThread has completed its operation. To mitigate this, we'll add a call to sleep and pass it a value of 1, which will allow both of our threads to complete their tasks before ending the loop. Let's go ahead and run this. And as you might have expected, our count is off. I'll run this a few more times, and while I do, notice that the values are different every time. This unpredictable behavior is happening because our threads are both accessing the same values and incrementing and decrementing them asynchronously. Here, we have our main thread running our loops synchronously. Notice that our first instance gets called, and our values are incremented and decremented before the next instance gets fired. Now let's add a second thread to the mix. Notice that our first instance call starts, and almost immediately after, our next call begins its work, both operating on the exact same object. In this video, we looked at how our threads can intermingle and disrupt our expected output. In the next video, we'll demonstrate how we can force our loops to behave as expected by implementing locks.